Hello everyone, welcome back to the Lesson BCE YouTube channel. Today I prepared how physics is applied in ballistic missiles. Stay tuned.
Hey everyone, and welcome. Today, we're going to talk about the absolute pinnacle of physics and engineering when it comes to launching something from point A to point B. I'm talking about the ultimate throw. That's really the core idea behind a ballistic missile. So let's break down the incredible science that makes it all possible.
I mean, just think about that for a second. What if you could throw something with so much power that it just goes up through the clouds, past the atmosphere, and travels thousands and thousands of miles to land somewhere else on the planet? Sounds like something out of a comic book, right? Well, that unbelievable feat is exactly what ballistic missile technology is all about.
And even though the tech is, unbelievably complex, the name itself comes from a super simple place. The word ballistic actually traces all the way back to ancient Greek from the word ballon, which just means to throw. So at its very heart, that's what we're talking about, launching something and just letting it fly, but on a massive planetary scale.
Now, it's really important to know that this throw is totally different from something like a cruise missile. A cruise missile is basically a pilotless airplane. Its engines are running the whole flight, it flies low, and it can make adjustments along the way. But a ballistic missile, it's all about that one single gigantic push at the very beginning. It gets an enormous burst of energy, and then it just coasts, completely unpowered, on a huge arc toward its target. And don't worry, we'll dive into the physics of cruise missiles in our next lesson.
So this epic journey, this ultimate throw, can really be broken down into three main acts, and we're going to walk through every single one of them. The incredibly powerful boost phase, the long, silent mid-course, and the final, fiery re-entry.
All right, let's start at the beginning. First up, the boost phase. This is where all the noise, all the fire, and all the drama happens. It's that one thunderous leap that sets the whole trip in motion. You can just imagine the ground shaking as those rocket engines roar to life, unleashing this unbelievable torrent of energy. And right from the get-go, the missile is fighting against two huge forces: the constant crushing pull of Earth's gravity, trying to hold it down, and the thick, soupy air of the lower atmosphere, creating a ton of drag. So, how in the world does it win that fight? Well, the answer comes from one of the most fundamental laws of physics out there. As the engines blast all that hot gas downwards, that's the action, an equal and opposite force pushes the missile straight up. It's Newton's third law of motion playing out in the most spectacular way imaginable.
And really, a rocket launch is like this complex dance of powerful forces. You've got that massive upward thrust from the engines going head-to-head with the downward pull of gravity and that friction from atmospheric drag. It's just a constant, brutal struggle to break free from the Earth.
To make that climb as efficient as possible, most of these missiles use multiple stages. Think of it like a relay race for rockets. The huge first stage does all the heavy lifting to get things off the ground. Then, once its fuel is spent, it just drops away, getting rid of all that dead weight. That allows the smaller second stage engine to fire up and push the now much lighter missile to even more mind-boggling speeds.
Now, here's the absolutely critical part. These first few minutes of flight are the only time the missile can actually steer itself. That's it. The onboard computers are working like crazy, making thousands of tiny split-second adjustments to the rocket nozzles. Because if there's any error here, even a tiny one, it could mean missing the final target by miles and miles.
Okay, so the engines have cut out. The fire and fury of the launch are over. Now the missile enters its second phase, a long, perfectly silent coast through the very edge of space. Welcome to the mid-course.
At this point, the missile is completely unpowered. It's now moving entirely under the rules of Newton's first law, the law of inertia. An object in motion stays in motion. Its fate is sealed, its path is set, determined entirely by the speed and the angle it hit at the end of that boost phase. It's literally just coasting now. For the next 20, maybe 30 minutes, it just silently follows this high, arcing path, a shape called a parabola. It's the same basic flight path that a baseball takes, just, stretched out over thousands of kilometers. With no engines, no steering, its only pilot is the force of gravity, pulling it along this perfectly predictable cosmic highway.
So after its long, quiet journey through space, the warhead begins its final and incredibly violent descent back to Earth. Let's get into the re-entry phase, because this is where things get really, really hot.
The warhead absolutely slams back into the atmosphere at speeds that are just hard to even comprehend. We're talking about potentially over 25,000 kilometers per hour. That's more than 20 times the speed of sound. Just wow.
At those insane speeds, the air doesn't just flow around the object, it becomes a physical barrier. It's like hitting a wall. All that kinetic energy, the energy of motion, gets converted into a staggering amount of heat through friction with air molecules. The temperatures can get hot enough to vaporize most metals in an instant.
So how does the warhead survive this absolute inferno? Well, it's governed by a super important concept in physics, its ballistic coefficient. Put simply, it's just a number that tells you how well an object can slice through the air. It's all about the ratio of its mass to its aerodynamic drag.
And you can really see the idea in action here. A sleek, heavy, dart-like shape has a high ballistic coefficient. It cuts right through the air and holds on to its speed. On the other hand, a blunter, lighter shape has a low coefficient and gets slowed down a lot more by drag. This means the warhead shape is absolutely crucial, not just for surviving the heat, but for making sure it stays accurate.
So after traveling thousands of kilometers, surviving that fiery plunge, how does the thing actually hit its target? Well, it all comes down to getting everything perfect right from the very beginning.
Missile accuracy is measured with a term called circular air probable, or CEP. Basically, it's the radius of a circle where you can expect 50% of the warheads to land. And getting that circle to be as small as possible requires unbelievable precision from the guidance system, all the way back in that very short boost phase we talked about.
But here is where this whole story takes a really fascinating and, frankly, a much more hopeful twist. The incredible technology behind this ultimate throw wasn't just used for weapons. The exact same science has a completely different and amazing application.
It turns out that ballistic missile technology and space exploration are really two sides of the very same coin. The powerful multi-stage rockets that were first designed for missiles were the direct ancestors of the rockets that launched Sputnik, the first satellites, and eventually the missions that carried the first humans into space. The guidance systems, the staging, the re-entry tech, it was all foundational for our journey to the stars.
So if there's one big takeaway here, it's this. The physics of throwing an object on this epic, global scale has completely shaped our modern world. From the tense balance of power in geopolitics to our greatest adventures into the cosmos, the legacy of this ultimate throw is absolutely everywhere. In the end, science and technology are just incredibly powerful tools. Their real impact depends completely on how we, as people, choose to use them. The physics is exactly the same whether we're reaching for another planet or targeting our own. And that really leaves us with a final big question to think about. What will our next ultimate journey be?